Please pause the video and try this problem. Now let's discuss the solution. We can start by numbering the carbons. Number all the carbons, including this one. There are no ionic bonds, so there's no formal charges. We can assign some roles. I see a neutral oxygen, which we can use as a nucleophile. Now we have to choose a leaving group. Well, here's a neutral iodide. That's a good candidate for leaving group. But what about this neutral oxygen? Could we use this neutral oxygen as a leaving group? Well, in the first video in this series, we learned that neutral atoms usually are not acceptable leaving groups. Now there are some important exceptions. Neutral chlorine, bromine, and iodide are good leaving groups, and neutral sulfonates are good leaving groups. But other neutral atoms are usually not acceptable leaving groups. That goes for oxygen. Neutral oxygens are usually not acceptable leaving groups. Now there are some important exceptions to that. For example, a neutral oxygen in a sulfonate is a good leaving group, but ordinary neutral oxygens are usually not acceptable leaving groups. The general rule is that neutral atoms are usually not acceptable leaving groups unless you have specifically learned otherwise. So it looks like we should not use this oxygen as a leaving group. Neutral oxygen is not an acceptable leaving group. That means that we would treat carbon 1 as our alpha carbon. That'll be a secondary alpha carbon. Now we can choose our mechanism. With a secondary alpha carbon, we'd be using the middle row of our table. And neutral oxygen in an alcohol is the left-hand column of our table. So we predict an SN1 mechanism. E1 would be minor, but the problem said to draw the substitution products. Remember that the S in SN1 stands for substitution. The E in E1 stands for elimination. So the substitution product would come from SN1 here. The only good leaving group in this molecule is the iodide, so the only carbon we can use as an alpha carbon is carbon 1. So and we'll use carbon 1 as our alpha carbon for this SN1 reaction. That's the main issue that I wanted to test with this problem. So what role is this oxygen going to play in this reaction? Well, basically zero role. The oxygen is just here, I guess, to confuse or distract you. But we're not going to, the oxygen's not going to play any significant role in our reaction. So now we can draw the mechanism for this reaction. The first step for SN1 is that the leaving group leaves the alpha carbon. That forms a carbocation on carbon 1. Now, in our next step, we should do a nucleophile electrophile step. Here is our nucleophile electrophile step. Now, the nucleophile is attacking a trigonal planar carbocation. So the nucleophile can attack from either in front of the page, leaving it on a wedge, or from behind the page, leaving it on a dash. This carbon is a stereocenter, so we get different products depending on whether we attack from in front or from behind the page. Of course, we don't make any changes to the configuration at carbon 4. Since carbon 4 is not participating in the reaction, there's no reason to make any change to the configuration at carbon 4. This stays as a wedge. Most important to get right is this positive charge. The oxygen started neutral and lost electrons, so it has to change to be positive. Now, it looks like we're not done because our main product still has a formal charge. So now we're going to do an acid-base cleanup step. Here are the electron pushing arrows for our acid-base cleanup step. Remember that a base is defined as something that donates electrons to take a proton. This is the right arrow to show a base donating electrons to take a proton. Don't forget to change the charge on this oxygen. It seems like now we are done because now our main products have no formal charge. So probably the professor would be looking for these two products as our answer. These would be considered the main products here that the professor is probably looking for. we can see that this oxygen basically just played the role of a distraction. It didn't play any role in the reaction. We knew it was not going to play a role because neutral oxygen is not an acceptable leaving group. My general advice is that you should make an effort to number all the carbons in all of your pictures. And I notice I didn't follow my own advice there. I numbered this carbon as carbon 7, but I forgot to continue to number carbon 7 in the subsequent pictures. So let's fix that. Let's put in some number 7s. So this is a better approach. We should number carbon 7 consistently in all of the pictures. And furthermore, it would probably be best to also give a new number to this carbon that we're using in the base. So let's call this carbon 8. And let's number that consistently in all of our pictures as well, carbon 8. Beginning students make the fewest mistakes if they make an effort to consistently number all their carbons in all their pictures. Please pause the video and try this problem. Now let's discuss the solution. We can start by numbering all the carbons. It's difficult to number these carbons because these are 3 separate methyl groups, so I guess I won't number those. There are no ionic bonds. Phosphorus is a nonmetal bonded to other nonmetals here. So these are covalent bonds, no ionic bonds, so there's no formal charges that we need to draw in. Nobody here has a negative formal charge, so we're going to have to use a neutral nucleophile. We can use the phosphorus as our neutral nucleophile because the phosphorus has a lone pair. We've learned that we can use a neutral atom with a lone pair as a nucleophile. And notice that phosphorus is specifically included on this list of a neutral atom that can act like a nucleophile because it has a lone pair. You should probably memorize this list of 4 atoms, oxygen, nitrogen, sulfur, and phosphorus, that are commonly used as neutral nucleophiles because of their lone pairs. Now we look for a leaving group. Well, we know that neutral chlorine can be used as a leaving group. Now, what about neutral fluorine? Is neutral fluorine an acceptable leaving group? Well, remember that neutral atoms are usually not acceptable leaving groups unless we've specifically learned otherwise. We've specifically learned that neutral chlorine, bromine, and iodide are good leaving groups. We've specifically learned that neutral sulfonates are good leaving groups. But what about neutral fluorine? We haven't learned anything specifically to tell us that that's a good leaving group, so no. We should assume here that neutral fluorine is not an acceptable leaving group. Neutral atoms are usually not acceptable leaving groups, unless you specifically learn otherwise. Neutral fluorine is in the same column of the periodic table as neutral chlorine, bromine, and iodide. Nevertheless, neutral chlorine, bromine, and iodide are good leaving groups, and neutral fluorine is not an acceptable leaving group. So that answers our question. We are not going to use the neutral fluorine as the leaving group. We'll use the neutral chlorine. Therefore, our alpha carbon won't be carbon 3. The alpha carbon will be carbon 4. And now we can choose a mechanism. We'll have to use our table to choose a mechanism. First, we have to notice that carbon 4 is a primary alpha carbon, and now we can use our table. We have a primary alpha carbon, which puts us in the top row of the table. Our nucleophile is neutral phosphorus. Here's neutral phosphorus in the middle column of the table. Middle column and top row puts us in this cell of the table, so we predict that the mechanism will be SN2. Remember that on the exam, you'll have to keep switching gears between different mechanisms. So you can't assume that all the mechanisms are SN1. You have to use the table to determine the mechanism. Let's again consider this fluorine. Could we use the fluorine as the leaving group for the mechanism? We know that fluorine is not a good leaving group. Therefore, no, we cannot use the fluorine as the leaving group for this reaction, and therefore we cannot use carbon 3 as the alpha carbon for this reaction. On the other hand, chlorine is a good leaving group. So we use the chlorine as the leaving group for the reaction, and we use carbon 4 as the alpha carbon for the reaction. Why was the fluorine included in this molecule? Basically just to distract us. It's not going to play any significant role in the reaction. So now we're ready to draw our mechanism. Now remember that the mechanism for an SN2 is a one-step mechanism where the nucleophile attacks the alpha carbon and the leaving group leaves the alpha carbon simultaneously. In SN2, the nucleophile attacks the alpha carbon and the leaving group leaves the alpha carbon simultaneously in the same step. Now we can draw the product from that step. Here's our product. Now the phosphorus is covalently bonded to these methyl groups, and there's no arrow telling us to break the bond to the methyl groups, so make sure the phosphorus is still bonded to all three of these methyl groups in the product. Most importantly, we have to change this charge. Remember, we always change two charges for every step. So we're changing the charge for the phosphorus at the beginning of the electron-pushing arrow series and the chlorine at the end of the electron-pushing arrow series. Since the phosphorus started neutral and it lost electrons, the phosphorus should change to a positive formal charge. The most common mistake that students make is leaving off this positive formal charge. But if you leave off the positive formal charge, your answer is completely wrong, because the most important thing to get right about the products is the formal charge. Now, is this reaction finished, or do we need another step? Well, usually we would expect that when there's a formal charge on our main product, we would usually expect that the mechanism is not finished. But we need to learn that SN2 reactions are an exception to that. Most professors would consider that it's okay for your final answer for an SN2 reaction using a neutral nucleophile to end up with a positive formal charge. So here we'll follow this exception. This was an SN2 reaction where it's okay to end up with a formal charge on our main product. So this is the final product of this reaction. What most professors like to do here is most professors like to draw the chloride close to the phosphorus to show an ionic bond between the negative chloride and the positive phosphorus in the products. Let's see. Well, for completeness, let's mention that carbon 4 is delta positive because it's attached to the chlorine, which means that carbon 4 was our electrophile. It's good to really label all the roles that all the atoms are playing and identify the clues that each atom plays that role, just so that you're building your Ochem skills. Notice that we don't make any changes to the configuration at carbon 3. Carbon 3 is a stereocenter, but it's not being inverted by this SN2 reaction. SN2 inverts the configuration at the alpha carbon, but not at other carbons. So since this carbon was not participating in the reaction, there was no reason for its configuration to change. And of course, our actual alpha carbon, carbon 4, is not a stereocenter. Since carbon 4 is not a stereocenter, it would be meaningless to try to invert the configuration at carbon 4. So the main purpose of this problem was to show you that if there's something like fluorine in the molecule, we cannot use that as the leaving group. As it turned out, we just ended up ignoring this fluorine for this SN2 reaction. Just like on the previous problem, we couldn't use this neutral oxygen as the leaving group for SN1. So we pretty much just ended up ignoring this neutral oxygen in this SN1 reaction. So if you see a neutral atom that you haven't learned is an acceptable leaving group, then you can't use that as the leaving group, either for SN1 or for SN2. That's the lesson from our last two problems. This problem also gave us a chance to get a little bit more practice with an SN2 reaction with a neutral nucleophile. Compare that with SN1 with a neutral nucleophile. When we do an SN1 reaction with a neutral nucleophile, the neutral nucleophile ends up with a positive formal charge, and then we do an acid-base cleanup to get rid of that positive formal charge. That's the normal pattern that you will usually encounter in other Ochem reactions. But SN2 reactions are an exception to that normal pattern. When you do a SN2 reaction with a neutral nucleophile, it also ends up with a positive formal charge, but then most professors usually would just leave that positive formal charge in the final product for the SN2 reaction. Mechanisms are usually not finished when the main product still has a formal charge, but SN2 reactions are an exception to that pattern. Please pause the video and try this review quiz. I hope you actually wrote down some answers to this review quiz. Here are the answers. I hope you understood that by the word roles, I was referring to nucleophile, electrophile, acid-base, and leaving group. Now, the electron donating roles are nucleophile and base. The electron receivers are electrophile, leaving group, and acid. I'll bet many people might have forgotten about leaving groups. Keep in mind that just like electrophiles and acids, leaving groups are also electron receivers, as you can see from the definition. Now, if nucleophiles and bases are both electron donors, then how are they different? Well, they're different because a nucleophile donates electrons to join the other molecule, while a base donates electrons to take a proton from the other molecule. And similarly, even though electrophiles, leaving groups, and acids all receive electrons, from these definitions, you can also see how they are different from each other. So you can see why you need two-part definitions for these roles. You need two-part definitions so that you can see how these roles are similar to each other, but also how they are different from each other. To succeed in organic chemistry, you must know this information like the back of your hand. This problem should have been boringly easy for you. If you didn't find this problem to be boringly easy, you need to keep practicing and reviewing these ideas until this type of problem is boringly easy. That's a crucial step for succeeding in organic chemistry. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.